Uh, Good afternoon, my lovely applied mathematicians. We've got 3 days left. I'm re-recording this. The original is up on the YouTube channel, but there's no sound because I didn't spot the little green, orange, and red thing. Wasn't happening in the mic channel when I'm recording. So basically, this video is just a kind of a brief walk through what to do if you feel like you're sick of just doing the past papers again and again and again, and it's boring, and maybe you don't feel like you're improving. It was a request from someone on the subreddit, so please don't hate them if they feel that they've done everything repeatedly. I suppose this would tie in as well with the video I'm going to post immediately after this one around how to use AI to help you study. So if you're coming up against something that's difficult, and you can't see why an answer is what it is, if the marking scheme isn't helping, throw the question into copy and paste the question into one of your LLMs that you use, and then ask it to explain it, and then ask it to explain the steps that you really don't get in detail, but I'll go through with that. So I suppose with this, I'm thinking also about how we can prep psychologically for the exam on Tuesday. And I think I would be expecting vectors to come up in a more nuanced way than previous exams. I know I've no evidence for this, and this is just me guessing, but vectors have been tacked onto questions at the ordinary and the higher level for the past 2 years. They don't seem to really know, I think, how vectors can be used in a mathematical modeling sense. So I reckon they're going to throw some vector thing there where you might need to start with the dot product and work towards an answer, or use some property of the dot product to help you get something, rather than at the end of the question, what's the dot product or what's the angle. So that's something to consider, that vectors may be more involved in the exam this year. Again, it could not be. I could be totally wrong, but I'd be surprised if they don't come up this year or next year, because they were a big important part, and to justify their place on the course, they'd need to be assessed properly. So now, if you've done all the questions and you don't feel like you're improving anymore, or it's just soul destroying at this late stage in the roasting hot June, I think we need to make it more exciting for ourselves, or interesting for ourselves, by challenging ourselves to investigate the possibilities of enhancing or adding on to a question. And I'll talk about this one where it has a ball of mass is thrown downwards into water, and another new version of Java. They were thrown downwards into water, and it experiences a buoyancy force, which is 4 times the weight of the ball, and a drag force, mv squared. And you draw your diagram, you create your differential equation, you solve that, you get answers for stuff, blah 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 blah. And towards the end of part 6 is make your differential equation for when the ball moves upwards. So the direction has changed, and it's now floating up, and will, in theory, I imagine, get to the top of the water. So you could challenge yourself by saying, well, how long, we know how far it's gotten down at the bottom. How long does it take to get back up to the top? And solve your differential equation in that way. You'll have to figure out what the boundary conditions are going to have to be, like the initial conditions, either the start or the end. But you can do that, and then you can get yourself an answer. And this is a sort of challenging yourself, because we don't have a marking scheme. You just have to see what it is you can do, and can you get an answer, and does it seem to make sense? And if it does, great, and you're prepping yourself for the unknown that you will have on Tuesday. The other thing then is, like, what speed will it have when it reaches the surface? and there's more, but I'd say if anything gets more complicated from that, they will give you a lot of scaffolding. So this question, anytime you see a Dijkstra or a minimum spanning tree, why not do all of them? So do Dijkstra here. You could do it in terms of like of a stock control thing. And if you wish, I will show you how you could use a stock control procedure to solve for Dijkstra as well. You could do Prim and Kruskal, do both of them, make sure you get the same answer. Just kind of expand, just make sure you can do everything for everything in this type of graph. So just if you want a stock control type solution for this, just let me know and I will do an up. This one, there's a challenge here which I presume is possible, but it's good to know to try things where you don't know. You are actually being a mathematician if you try and do something where you don't know the answer. So P and Q thrown or fired or whatever, and they collide in midair, and you have to show the stuff, and you get answers for when they collide. So what I would think about this is, how far apart are the balls then when they hit the ground? So they've collided, and then they have a collision, and which we know how to model collisions, which is to do with principle of conservation of momentum and Newton's experimental law. We know if they're in the same position, if they collide, they have to have the same height, so the collision is along their horizontal. So their vertical velocities stay the same, their horizontal velocities change, and that will be in terms of E, the coefficient of restitution between the two particles. And you can work out then the new velocities of both of these particles. Like if they collide this way, then they're going to bounce back and go that way. And then you could find out where they land, and then how far apart are they when they land. So it's a way to embed different aspects, different parts of the course together into one big question. And it does, I think it should prep you for the complicated stuff that's going to happen. As much as we can be prepped, the point of this course, I think, is that you will have to see the unknown. So using your kind of creativity to come up with what unknowns could be is a great way to prep for the eventual madness that you're going to see on Tuesday. You could, from this type of diagram, instead of doing a early time, late time chart and getting the critical path, you could immediately go into a Gantt chart, get your answer, and then do your early time, late time, and see does the Gantt chart agree. It's good practice just in case a Gantt chart comes up. I like this one. Again, I'm speeding through all these things just because I know you have the ability to press stop. So there's a little toy car and it does a loop-de-loop, and you have to figure out stuff about that. But what if, instead of the toy car falling off the track, what if the toy car was attached? So what was the minimum speed it would have to be to actually get all the way around? So it would have to get up to the top. It wouldn't need to not fall off because it is attached, but it would need to get up to the top and then keep going. But then what if there was a little toy person in the little toy car, and at the very top of the loop the little toy person fell out? What speed would the toy car have to be going to perfectly catch the little toy person at the bottom of the loop? And is it possible? So it's a silly situation, but the maths in it is quite complicated and possibly interesting. So think of silly situations that might be interesting to model mathematically. One of my favorites would be we'll get to that problem later. So a spherical bob. So this is a circular motion and things just flying around in the air. What if instead of being in the air, M was on the string, but it was also on the surface? A flat horizontal surface, or the inside of a sphere, or the inside of a cone. There's lots of different things you can think of and different ways you can kind of add complications to what you're doing. And what if there was friction? Obviously, if there was air resistance here, I imagine it would kind of slow down and stop very quickly. But why not see what would happen if there was air resistance? It might be an interesting thing. Is if there's air resistance, which in real life, gradually the radius of the circle gets smaller and smaller and smaller. And can you model that in some way? And I don't know how. It's not something I've done, but I'm just trying to throw ideas. So if there's air resistance, it's causing your V to get smaller, which means that the OR has to get smaller. So gradually your radius is getting smaller and smaller and smaller. And the thing, instead of doing a circle, it does a spiral. And I think it is possibly beyond what we need to be able to do for the exam. But why not try and see if you can do something? Because it is just, if it doesn't work with just the maths we know, then that's good. And if it does, then that's really cool. For something like this, could you turn that into an adjacency matrix? And then, I suppose, can we learn something about that and what it would look like? Remembering the adjacency matrix just is a ones and zeros for how many connections there are between various paths, between various nodes rather, sorry. Can you solve this without the algebra hint? It might be possible, it might not. I haven't tried, but it can't hurt to try. Challenge yourself to come to understand the limits of what we know. This question where you've got a motorbike and a car, and you have to calculate the greatest distance. Now, the easiest way I think it can be done is to find when two things are going the same speed, because after that time the motorbike is going to catch up, and before that time it's going to be the car is going to be accelerating away. So it's when they have the same speed is when one is furthest away from the other. But can you do it with calculus? And I think you can, because if you got a function for the distance between the two, differentiated that, found a turning point, that would be where the distance is greatest, I think. And we can get the answer from the marking scheme, so you can see does your calculus work. So there's a nice safety net there that you know what it should be. You don't know how the maths is going to work, but you do know that the answer is what it is. So that could be cool. If anyone out there tries any of these things and has success or failure, I'd love to hear about it. This one, it's vertical circle, but what if there was friction? How would that change the equations? How would that change the answer? Genuinely don't know, but it'd be cool to find out. This one, you can. What if B hits the ground first? What's the speed of D? What if D goes above the pulley first? What's the speed of B? Just put numbers in and then see what happens, because the question is very theoretical in that we don't know how long the strings are. But what if we did know how long the string was? And we're going to come back to this question actually in the next video as well. This one where we've John and Kevin cycling, what happens is John is behind Kevin. What happens then? John overtakes Kevin, But because Kevin is accelerating more, Kevin then overtakes John and goes on and wins the race or whatever, is always ahead. But can we change the speeds, either of the speeds or either of the accelerations, so that John never overtakes Kevin or Kevin never overtakes John? And I think it's possible that you can tweak it so maybe they are at the exact same point at some point, but that you never have an overtake. I think if you have one overtake, you have to have the other one, I think. But it'd be cool to find out. Now, you'd have to keep Kevin's acceleration would always have to be more than John's. That's the only way we can get them to overlap at all, I think. But can you do it so that that John never catches up is one possibility? Or can you have it that they meet only once? So it's worth investigating how you might even do this to kind of open your mind in advance of Tuesday. This question, this one could be cool or impossible. So you got a car pulling up a Jeep up a hill. What if the friction force was gradually reduced? So the friction force. So I suppose what if I'll say that again. Not the friction force. What if the engine, the force exerted by the engine that it could exert on the hill was less, and got less and less each time because the ground got slippier or the wheels filled up with mud or whatever. So instead, the friction would still be there pulling it downwards, but what if the engine couldn't gradually put its, if the wheel's turning, just had less and less and less of an effect on moving it upwards. So that 400 slowly reduced. At what point would it start falling downwards, etc.? So, and it turns a connected particles question into a calculus question and links the two together. So that could be cool. I'm reminded of there's some crazy sport of driving buggies up really steep hills, and eventually it's almost vertical, and the odd car can manage it. But anyway, so just that idea that what if, because the wheels, say, filling up with mud or the ground getting wrecked, that the wheels couldn't actually grip enough onto the slope to do anything. Or you could have what if the slope gradually increases, and how would that work? And how would that look with one of these things? Snowboarder question. So I suppose with this one we have no friction because there's very little friction on ice. So what would happen if, say, the snowboarder goes up into the air, does it like a 360 or whatever the hell they do, it goes back down, and then if it wasn't a half pipe, if it was a quarter pipe and it went the other way and it kept going back and forth, how many of those would have to happen if air resistance slowed the snowboarder down every time? What is the maximum number of jumps that the snowboarder can do before they're stuck in the pipe forever, before the air resistance slows them down enough so they don't have enough speed to get up over the edge? And who knows, it might be easy to model, it might not. There might be an obvious pattern, there might not, but it's cool just to examine the possibilities of what you can do. Now there's a couple of cool options here. What's the furthest distance that Fiona could hit the slitter? You can find it out, and you can prove it, and you would have to use calculus to find a turning point. And so I will say nothing there, but it can be done, and the answer will be obvious, I think. What is the highest that Fiona could hit it and still score a goal? So how could we do that? Now there's one I don't know how this works or how easy it is. What if we included air resistance? She hits the ball and it moves through air, and there's a resistance of like minus kv squared or whatever, the usual type of thing you get. What would happen? And you'd have to remember that resistance opposes motion. So the resistance would be constantly changing because the direction of the ball is constantly changing and the speed is constantly changing. So there could be way too much stuff going on there if you have air resistance, or maybe there isn't, but why not investigate and see? It will also give you an idea of what they probably won't ask. Now this one, again, this is a very much throwing an idea out there, not knowing if it's relevant even slightly. We have water leaving a tank. Is there some way we could understand how gravity affects the flow of water? So we have a rate of escape for water. What if we were on the moon or on Mars and we had the same water in the same tank? Would it flow out at the same rate? And I don't think it would, which would mean gravity has to have some effect on this, but how and what? And can we model this with the physics and maths that we know? And we might not be able to, but understanding the bounds of your subject can give you insight into what could be asked on Tuesday. So if you guys try any of these things and you get anywhere, I'd love to see it. And if you get nowhere at all and you want me to get you started, just give me a shout and it'll be interesting to explore that stuff. Cool.